Hello, my name is Adarsh Narayanan, and this is Lab 3 Black Hole and Orbits. Introduction, Part 1. First, we need to analyze the motion of a star to determine the mass of a black hole. After this was done, we calculated that the MBH equals 1.43 times 10 to the 34 kilograms. In Part 2, we used that calculated mass of the black hole to determine the initial velocity of a spaceship to get it close enough to the black hole without crashing and still being able to leave the system. So through trial and error, we got these values. The speed in the x direction is negative 200, and our speed in the y direction is negative 500. This lab will demonstrate the effects of Newton's second law and its relationship with momentum. Our fundamental physics equations. Newton's second law. For this one, we want to create the F parallel and F perpendicular to get F net. So to do that, we take the derivative of the change of momentum or a change in time, and then we use the product rule to separate the two. This creates the specific parallel component and perpendicular component. For the gravitational force, the system is the star, the surroundings is the black hole, and the equation between them is that F grav equals gm1 m2 over r squared times r hat. If you take the derivative of the two, then you get this formula, and then you can move around components to get mass of 2. And this is what you get. This is what the mass of the black hole would be, and this is what we will calculate in the first part. Part 1. For our glow script model, we had to use our personal email to create unique values for our seed. The initial conditions are listed: our gravitational constant, mass of the star, and time interval. And then we have the calculations for the star velocity. All these calculations give us the star velocity that we will need for our calculations. And then this, in the while loop, we need to iterate through each equation to finally get F perpendicular and then F parallel to get F net. And then we use those values to get the mass of the black hole using the formula that we're deriving in the previous slide. I also created count and average values to calculate the mass of the black hole. I got every single value that was shown in the after you run the program. I added them up and divided by how many there were, and we got the average. This is our results. This is what the program shows while it's running, and as you can see all the values of the masses, and we want to average all of them. Okay, so now you can see F net parallel and F net perpendicular, and if you add the two of these vectors, you get this vector, which is F net, and you can see the average value of the mass of the black hole, which is the same as what I originally said, which is 1.43 times 10 to the 34 kilograms. Alright, part 2. For our glow script model for part 2, we have a ton of constants, which is the gravity constant, the mass of the planet, mass of the moon, mass of the ship, and then delta T. So our initial conditions for the moon is listed here, and we want the initial planet speed and velocity, initial spaceship speed and velocity. And also, we also have these values that I stated before. These are used and calculated through trial and error. Alright, for our while loop in the second part, we need to get the forces on planet by moon and ship, the forces on the ship by planet and the moon, and then we iterate position from velocity and net force, which is shown here. Alright, our results. The ship location is 7.13 times 10 to the 8th meters away from the planet. The moves circularly. The spaceship moves elliptically. Some sources of error. So we have some round-off error because of some loss of precision in calculations, assumed physical emissions like non-gravitational forces, point mass and fixed center assumptions, and then, of course, trial and error to find the initial velocity. What if, and what does it mean? How does the net force and its parallel and perpendicular components differ from the change of momentum and its parallel and perpendicular components? According to Newton's second law, F net equals dp dt, the parallel component changes the magnitude of momentum, while the perpendicular component changes direction. In real calculations, small differences can appear because of approximation. In this lab, we can use dp/dp instead of F net since it let us solve for mass directly. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? The model must include all objects, planet, moon, and spaceship, and the gravitational forces between them. It also needs each object's mass, position, and velocity so their motion can update over time using Newton's laws. The planet's gravity will have the biggest effect because it has the largest mass. Thank you for listening to my presentation.